Hi, welcome to this webinar on zMAX Essentials, Optical Design and Stray Light Analysis. So a brief introduction. My name is Sophia Fox and I'm part of EDRMedeso, who are the leading supplier of simulation technology and consultancy in the Nordics and UK, and we're a channel partner for Ansys. So the agenda for this webinar is in 4 parts, and I focus mainly on sequential mode. The first is a quick introduction to Optics Studio in sequential mode, so some definitions and using the interface. Next, I'm going to jump straight in with the simplest example to demonstrate some of the immediate features of zMAX. And then I'll move on to a more complicated imaging system example, the double Gauss, where I'll go through the design process. Finally, I'll briefly demonstrate the alternative mode in zMAX, non-sequential, which for this application will be for stray light analysis. So to just clarify, zMAX supports 2 modes. There's sequential mode, where the rays of light, they don't split. They're traced from one surface from the object plane to the image plane in a sequence of surfaces defined in this lens data editor window here. And then there is non-sequential mode, which is more of a brute force approach, where basically you have sources that emit the rays and you let the rays just bounce around and hit objects and detectors in a 3D system. So in this mode, you could model the ray splitting, scattering at the surfaces, this sort of thing. There's also mixed mode supported in zMAX, where you model different parts of the system in sequential and non-sequential mode, but I won't go into further details on this here. So let's jump straight into zMAX. So here I've started zMAX from the Ansys Optics launcher. I have the following for sequential mode. There's the lens data editor window here, where the sequence of surfaces are defined. So you've got the object plane, the image plane, and there is a surface labeled as the aperture stop, which is the aperture that limits on-axis rays. And this determines the amount of light reaching the image. So the stop can be a separate physical stop or a lens aperture or something like that. Before creating the surfaces, however, you should define your system settings in the System Explorer here, especially your system aperture. So this defines the object space entrance pupil diameter, or size of your ray bundle on axis that enters the optical system. And zMAX supports 6 definitions, and which one you use depends on your application and needs. Similarly, you can define your fields in the System Explorer. So each field is a bundle of rays entering the system, and they can come in at a specified angle, object height. So if we open the field data editor here, so there are in fact 5 definitions. So for example, if you're building a camera to look at the far field, you might want to specify your fields in terms of angle. Or if you have a specific camera sensor, you might want to specify the fields in terms of the image height. So all this is to make things easier depending on your optical system. And then there are other important settings, the wavelength, for example. So zMAX has a lot of built-in presets of different spectroscopic lines, visible and photometric values that you can select. You can model for different temperature and pressure that will impact the optical properties. And regarding the optical properties, zMAX has a vast material catalog library that contains refractive index data of many glasses provided by vendors, and you can also build your own. And then here, you can define or change your system units. One thing to note, however, is wavelength is always defined in micrometers, no matter what you set here. And then up here is the ribbon toolbar, where you can access tools to do with the design setup, analysis, optimization, tolerancing, and many of the different libraries. So I won't talk about a lot of these, but just know that zMAX has lots of flexibility, inbuilt libraries and presets to make design much easier. So I'm going to do the most simple case, which is a single lens defined by 2 surfaces. And these are some example specs. We want an entrance pupil diameter of 20 millimeters. We also want an F number of 4 and the center thickness of the lens to be between 2 to 15 millimeters. And the edge thickness must be larger than 2 millimeters. We'll use NBK7 glass from the SHOT catalog, and we'll use a single wavelength. So here we take the spectral line at 587 nanometers. Let's also assume the object is located at infinity. So we have collimated rays entering the system, and I'll assume we have one field incident 0 degrees with respect to the optical axis. So let's go on to Optics Studio. So what I'll do is first enter everything into the System Explorer. So the entrance pupil diameter is 20 millimeters. We want on-axis fields, so it says check that's at 0 degrees, which it is. We want the D-line presets, so we'll select that from here. And then I'm just going to check that we are looking at the shot material catalog, and this contains the NBK7 glass. Okay, so while building anything, I like to have a cross-section schematic to check what I'm doing in the lens data editor. So I'm going to open the cross-section layout here and dock that here. So in zMAX, you can move windows around to however you like. So I'm going to insert a surface after the stop, so Control Insert. And so these will be the surfaces of my lens. So in zMAX, you can have many different sequential surface types here. And if you want to know more about any of these, zMAX has a very good documentation on everything. So you'll notice on every window there's a help icon here, and you can click on that, which takes you to the specific chapter in the help system file here. So in fact, let's do that. So we go to there, then data editor, let's look at sequential surfaces. And here we have a list of all the sequential surfaces. And if we click on one, it tells us how to implement it in Optics Studio. So I'm using the standard surface, which is a conic A-sphere. So each column for the surface are the surface's parameters, such as radius of curvature, thickness, etc. And you can design your lens as a function of these. So I've also set the conic constant to 0 so that we have a spherical surface. So I'm going to start defining the lens. So I'm going to give it a positive radius of curvature of 100. So the center of curvature is on the right of the surface. I'm going to give it a thickness of 10. I'm going to use NBK7 glass for the material. And then I'm going to do the second surface of the lens, minus 100 radius of curvature. And then the last thickness, this defines the distance from the back of the lens to the image plane. So I'm going to set this as 50. You can check the surface profile with tools in the analysis tab here. So there's a bunch of surface tools where you can look at the sag of the lens. So if I hit sag cross section, and this tells me that I've got a spherical surface on surface 1, the front of the lens. At the moment, the aperture stop is the first surface of the lens, but I'm going to define a separate stop surface. So this would be a physical stop, and having an added stop to a system can be used to improve image quality, for example. So if I hit this, click Insert, I'll make this 50 millimeters from the front of the lens. And then to define this as the aperture stop, I can go on the surface's properties from this drop down, make a surface stop. And there we go. It's not showing on the layout, so I'm just going to change the settings on my layout window, look at all the surfaces, and I want to look at all the rays, not just the chief and marginal. And there you have it. Now, the lens data editor looks very similar to an Excel spreadsheet, and in fact, it has similar properties. For example, you can use solves, which calculate the values of cells based on the values of other cells, ray data, or some constraint. So in the specs, I think, we needed to ensure an F number of 4. And we can set this by setting a solve on the radius of curvature of the second surface, like so. So you can see, depending on the parameter, there'll be different types of solves. We're going to select the F number, set this to 4. And what this has done is adjusted the radius of curvature to maintain an F number of 4. Another useful analysis tool is the prescription report in reports here, so prescription data. And this gives a nice summary of your design specifications. So what we can see immediately is that the image is not at focus. So we can view where rays coming from a point from the object hit the image plane, or in fact any surface, by going on the Analyze and going on the standard spot diagram here. So I'm just going to adjust this to 25 so we can see better. And we can see that the root mean square radius of the spot is over 2,000 microns. There is a nice tool in zMAX. If we go on the Optimize tab and click Quick Focus in the Manual Adjustment section, and what this does is adjusts the back focal length, or the last surface thickness, for best focus or minimum RMS aberration. And there's different criteria. I'm going to select the spot size, hit OK. And we can see that the RMS radius has reduced to 50 microns. And if we go on the layout, we can see that the thickness here has, or the distance to the image plane has been adjusted. If we zoom in on the focus, the rays don't actually arrive at a point. In fact, some rays focus in advance of rays through the center of the lens along the optical axis, and this is actually spherical aberration. So let's resize that. So zMAX has a whole bunch of tools in the analysis tab to quantify the quality of the optical design. So there's the ray plots. You can calculate the exact wavefront error with the OPD plot. There's a wavefront error here, and MTF. So there's a whole bunch of tools to help with this. I like to use the sidle chart or sidle diagram here, which shows the third order aberrations as you go through the system. So this analysis is fast, and it can be a nice way to kind of do inverse design as you work out where the biggest aberrations are coming from and how to remove or correct for them. So these are the 5 sidle aberrations, and we can see that spherical aberration is dominant. So when you have rays entering the system off-axis and different wavelengths, you will have higher values, for example, of distortion and chromatic aberrations. So let's add more wavelengths and fields to see this. So if we go on the presets, we use the RGB visible, and then we'll add a field. So add field. So let's just check the layout, 5 degrees. And here you can see that another bundle of rays are entering the system at 5 degrees with respect to the optical axis. So let's look at the spot diagram. The RMS spot size has increased. Actually, no, what I've done is I've forgotten to actually select the preset. There we go. So we can see that the spot size has increased from to 74 microns for the on-axis and 140 microns off-axis. And you can see this comet shape here, which is often which indicates a coma aberration. And let's look at the sidle diagram. And indeed, we have some coma. There's some distortion, and we have a longitudinal and lateral chromatic aberration. So I won't go through all of these in detail, but there are a large number of analysis tools for your optical system to save on post-processing. So for the design phase, we want to optimize our system. And in order to do that, we need to define the merit function that needs to be minimized. This is typically a specification that we can measure of the intended performance. So we've been using the RMS spot size, and I'll keep using that. But we also want to tell zMAX which parameters we can vary to minimize the merit function. And we do this by simply setting those parameters as variable solves, like so. So we want to vary the position of the stop, so we can do Control Z, radius curvature of the front of the lens, and the thickness, and also the back focal distance. We can't make this a variable because it's already fixed by the F number solve here. Once we've done that, we can go on Optimize. We can open the merit function editor. And you'll see that this is a blank spreadsheet, but what we can do is to fill it in is open the optimization wizard. So let me just increase this so we can see everything. So we want to optimize for RMS spot size here in the criteria, and we're also going to set the boundary values for the glass. So I think it was from 2 to 15 millimeters with an edge thickness of minimum edge thickness of 2. So these are center thicknesses of the lens, and then I'll just set boundaries on the just for good practice. Okay, so let's hit OK. And what we've done is fill the merit function editor with rows of operands, and they're these 4-letter names, which are values that zMAX computes, and they're assigned. Let's adjust that. They're assigned target values and weights. So the higher the weight, the greater contribution it has to the merit function minimization. So these are the operands that set the glass and air boundaries. And these are the operands that calculate the transverse aberrations, or how far the ray lands from the centroid of a spot. You can see that their target is 0 and they have a variable weights. So there's around 350 operands, and they're all documented in the help file. If you can't find the one you need, you can also write your own. So the merit function is calculated here as 0.034. So let's see what happens if we just hit optimize. So there's 2 algorithms. There's a damped least squares and orthogonal descent. So I'm going to stick with DLS, as this is most commonly used for sequential. I'm going to hit start, and let's exit And let's look at so here we can see that the lens parameters have been adjusted. And then if we go on the spot diagram, let's just make that bigger. We can see that the spot size is reduced from 74 to 60 on axis, and it's been over halved for off axis from 140 microns to 67. Now, as I said before, there are a lot of operands, including ones that calculate the aberrations, and you could include these in a merit function as additional rows. But what you'll find is there's not a lot one can optimize with a simple glass singlet, and to optimize further, you'd want more degrees of freedom, such as extra surfaces, as aspherical lenses, changing the glass, and so on. Another thing I forgot to add is if you're having any issues, zMAX has a diagnostics tool in the setup called System Check, and this provides a report of memory use errors and warnings. So we're going to move on to a more complicated design and highlight how zMAX can speed up the design process, like so. So in the design stage, especially if you're new to it and need multiple elements and components, it can take a lot of time to set this up and to meet demanding specifications. In order to avoid reinventing the wheel, zMAX Premium has a library of design templates ready to use. So let's demonstrate this. So if we go on Libraries, Design Templates. So there are currently 642 pre-built designs, and we can filter them in the search criteria here to find designs that meet our needs. So for example, if we want a system working in the visible wavelength, so we can set the range of that from 0.4 to 0.7 micrometers. And then if we want a relatively fast lens, so let's say a working F number from 1 to 3. And say we have a limit on the number of elements or lenses in our system, let's say 6. And these are a list of designs that meet our criteria. So in addition, zMAX has a large number of example files located in the zMAX folder and documents. So in the design step, we've cut out a bunch of work and started with a proven design. So I'm going to select the double Gauss. And this is used in SLR cameras, and there are a large number of variants based on this design. So if we have a look at it in setup, let's go cross section. Let's look at all the rays again. So here we have 6 elements, including 2 compound lenses with a stop in the center. So there's many degrees of freedom. And if we look at the Seidel diagram in aberrations, you can see how the symmetry of the system works to cancel out aberrations, and they're minimized quite nicely by the time you get to the image plane. So let's say you have the following specifications of a system, and we are using a double Gauss to image onto a film or sensor, which is 24 by 36 millimeters. So when we define the fields, we will use the diameter equal to the diagonal of the sensor so that the fields cover the whole sensor or image plane. So we'll define our fields differently this time in terms of image height. We require less than 1% distortion, and we have similar limits on the lens thicknesses. And we want a minimum back focal distance of 40 millimeters. So this might be to allow for more room of other components later on in the design. And then now we want to optimize the design for the following MTF or modulation transfer function goals rather than the spot size this time. So because this is a camera application and the image is formed on a detector, we're using MTF as this quantifies the image quality in terms of resolution. So due to my background, I think of MTF as similar to the bandwidth of a filter in electronics, where the frequency is the spatial frequency in line pairs or cycles per millimeter, and the MTF drops as spatial frequency increases because the optical system can't differentiate between line pairs so closely spaced apart. So aberrations and diffraction will limit the MTF of the system, and MTF will get worse for off-axis rays. Okay, so let's adjust our current design for the specifications. So we want an entrance pupil diameter of 25 millimeters. To set the fields, I'm going to open the field data editor. I'm going to delete these a drop-down menu, a field type. We want it to be image height. In the fields wizard, I'm going to set equal area Y fields. I want 3 Y fields, and our maximum will be 21.6 for our field. So 21.6 here. Let's click on OK. And so I'm just going to sort these in ascending order so that the maximum off-axis field is field 3. Okay, so I'm going to set for the visible preset here. So select preset. It's been adjusted. And this U-solve, it fixes the diameters of these lenses so that they have fixed apertures, but we want these to float. So I'm going to remove the aperture by clicking on this ring and remove all apertures. And then we want an F number of 3. So I'm going to put an F number solve on the last surface, like so. And then I'm going to look at the layout, and we see it's out focus. So if I go on optimize, quick focus, like so, and there we've adjusted the back focal length. So now let's look at the MTF. So if we go on analyze, MTF here, let's just set the maximum spatial frequency we'll look at to be 50. And so you can see that the performance is very poor and does not meet our specifications. Okay, so we're going to do optimization to improve this, and the merit function has a special criterion to directly optimize the MTF much faster. So I'll go on the design. So if we start the merit function editor here, if we open the wizard, optimization wizard, so we select contrast from the criterion. Our highest spatial frequency of interest is 50 line pairs. I'm going to increase this to 4. So this will sample more rays and allow you to resolve higher order aberrations and in the wavefront error. There are now limits on the lens thicknesses, so minimum center thickness of 2, 12, and then make that 2. And then I'm also going to put limits on the air, like so. So I'm going to hit OK, and that looks fine. So if we scroll down, these are the boundary operands, and here we have these MEC operands, and these are used for the contrast optimization. Now with imaging off-axis rays, distortion increases. So let's look at distortion here. If we go on Analyze, Aberrations, Field Curvature and Distortion, and here our distortion is it's over 3%, and we have a limit of 1%. So let's go on the merit function editor, and we can add operands to the merit function editor to optimize for this too. So I'm going to just going to add a bunch of rows. So like so, and the operand for a distortion is DIMX. So this is for off-axis field. We want the off-axis field here to be 3. We want this to be 1%, so with a weight of 1, so it contributes to the merit function calculation. And then we have a minimum back focal distance of 40 millimeters, so we can use the center thickness greater than operand on surface 11, I think. Yep, 11 here. Center that like so. And our target for that is 40 millimeters. And again, we want to give it a weight of 1. Okay, and then we have the conditions on the MTF. So the operands for these exist, and I'll enter them here so we can see what the values are. But I'm not going to give them a weight or let them contribute to the merit function. So I'm going to give them a weight of 0. So MTF average MTF, let's just make that 2. Field, on-axis field, our spatial frequency here is 30 line pairs, and this was, we wanted 65%. And then for the 50, the higher spatial frequency on axis, we want 50 line pairs. We wanted a performance of 40%. And so off-axis MTF, this field 3, we're looking at 30 line pairs, and that was going to be 0.55. And then for the other spatial frequency, which was 45 line pairs, field 3, 45, and this was a performance of 0.4, like so. So the reason I'm not giving them weight is because the contrast optimization will hopefully satisfy these conditions anyway. And if not, we can weight them later. So then if I hit optimize, oh yeah, so I've forgotten to do this. So I also need to tell zMAX what I want to vary. So I'm going to tell zMAX to vary these for the optimization. So maybe I have curvature here. Control Z, and then all the thicknesses and positions of the surfaces here. So now I'll click optimize. Hopefully this will work now. Okay, so you can see the merit function has reduced massively actually to 0.041, and let's click exit. And we can indeed, so our distortion is very close. It's basically 1%, and our MTF is well beyond the specifications. So this optimize function performs what's called a local optimization, which means it searches for where the gradients decrease nearest to it, and so it'll find its local minimum. The problem is this method's highly dependent on your starting value, so it might not give you the global minimum. So zMAX has two global optimization tools. The first here is global search, which I won't do here, but the idea is that you have a rough design that's very complicated, and you run this usually overnight or something like that, and it'll explore all of parameter space. The other is a hammer current. And this is as it sounds. It starts from an existing design and hammers away looking for any other minimums in the merit function. So until you tell it to stop. So I don't think it's going to find anything else. So I'm just going to hit stop and exit. So that's really the gist of the optimization. Another useful analysis tool actually is image simulation. And extended analysis, image simulation here. And this is quite good to communicate to non-technical persons the image aberrations. So actually let's change the, I like this one because it's cute. There we go. Now, we could take this design and build it, but in reality, there will be deviations from the ideal. For example, with the manufacturing of the lenses and assembly errors when you mount the lenses in a mechanical setup. So all these will reduce the performance or image quality. And if you immediately take the design with the lowest merit function, this could actually be very sensitive to these errors. So for example, if we go onto the sidle chart, so you can see that the distortion is quite high in parts of the system. So any tilt and offsets of the surfaces and elements will upset this balance of power and could potentially degrade the image quality by a lot. So what you want to do is to select the best manufacturable design with the lowest merit function. So the purpose of tolerancing is to determine the amount and type of manufacturing errors that are allowed in the built system, but also maintaining the system performance to be within the specifications. So to do this, we do the following procedure. We optimize our design, which we've done. We define initial tolerances and criteria. So here we basically look at what can go wrong with the design and by how much when it's manufactured. How does the design vary with tolerances? And is this acceptable? And then if it's not acceptable, we need to adjust tolerances, compensators, which is any parameter which you can vary to relax the tolerances within a set range, or you need to adjust the design until you get the acceptable performance. So for our double Gauss, I'm just going to assume the following tolerances. So we have curvature errors on all the lens surfaces. There's variation in their thicknesses and surface irregularities. And then if we make the assumption that the lenses are mounted on their back surface, there are 4 surface offsets or tilts, which will represent as a deviation edge thickness. We'll also assume a tolerance for the refractive index and dispersion of all the glasses. And then with the assembly errors, let's assume the element tilts vary between plus or minus 0.1 degrees, and the element offsets in X and Y vary by 0.1 millimeters. We'll also define a compensator, which will be that 40 millimeter back focal distance, and we'll adjust that by plus or minus 2 millimeters to correct for tolerances. Okay, so we can set these up in zMAX using the tolerances data editor. So if I go on tolerance data editor here, and it has the same format as the merit function editor. So we can go on the tolerance wizard. We use the tolerance wizard to set up a semi-automated tolerance model in which a set of default tolerance operands and their ranges are applied to surfaces and elements in the design. So deciding where to start can be challenging. when it comes to tolerance ranges, and zMAX has several presets that categorize tolerances into tiers of cost or difficulty, and it also contains charts from several vendors like Optimax and Edmund Optics. So for example, if you change the grade from commercial to let's say high precision, you'll see that the tolerances have been tightened. So I'm going to select commercial grade. I'm going to use OptiMax, select this preset. So it's updated with surface tolerances for the lenses. And then I'm checking use focus compensation, and this will automatically define the back focal distance as a compensator, which will be adjusted during tolerancing. And then I'm going to add the assembly errors. So we want offsets and tilts. So 0.1 millimeters and 0.1 degree for the tilts. Make sure we look at all surfaces, so hit OK, just the width. And as before, the tolerance wizard has populated the editor with tolerance operands. So if I hit on 1, so we have nominal values of the parameter and of the tolerance, and their range defined by the min and max here. So all this is automated, but zMAX provides lots of other options for tolerancing if you have a very complicated design and need more flexibility. So you can use user-defined tolerance operands, and you can also write tolerance scripts here, which provide a lot of flexibility for the tolerance criterion and compensators. So here we have our tolerances, but we need to do a few tweaks. So because our thickness of surface 11 is already being adjusted, we need to remove surface 11 from these thickness tolerances. So here the surface 11 is being adjusted. So we'll just look at surface 9 without any adjustments to the other surfaces. And so we're tilting the front face only, so they correspond to these operands. So if I look at the layout, so we want to tilt surface 1, so we'll remove surface 2 tilts. And then 3, I think we want to tilt, and we'll delete the 4, 5. And then in the layout, we want to tilt that surface, so we'll fixing 7, so we delete 7 and 8. I'm able to select it. Leave 9, and then we're deleting 10 and leaving 11 of the last singlet. Okay, so that looks good. Another thing is you should remove any variable solves before you do tolerancing. So I'm going to remove these. The idea is that you want to tolerance the system as is. You don't want anything changing because this would be what you'd manufacture. So undoing variables here, Control Z. And then I'm going to also move the thicknesses. I'm then also going to fix the apertures. So I'm going to go on the ring here, convert to circular aperture. So now they're fixed. And then I'm also going to float by stop size so that we fill that stop. So now we need to decide the tolerance criterion or figure of merit, and this can be anything you want really, including the optimization merit function. And you can define your own, but it's recommended to be something you can measure, like the RMS spot size, wavefront error, MTF, something like that. The important performance metric for evaluating the system is the MTF across the field in this application. And we've already written most of this in our merit function. So I'm going to actually copy these rows. See, then I'm going to delete everything. And then I'm going to paste. Excellent. So then what I'm going to do is instead of actually using these directly in the optimization, I'm going to use the operand greater than function. So actually we want to control insert. So operand greater than. And what I'm going to do is, so the operand is MTFA. I'm going to use operand greater than so that these only contribute to the merit function when they're out of spec range. So let me just resize. So when this is out of 0.65, you could also make these a higher value if you really wanted to tighten the system. So operand greater than, this is operand 4. We want that more than 40%. Control insert, operand greater than, and that operand is 6, and we want that more than 0.55. And finally, operand greater than for operand 8. and we want this more than 0.4. So, and I also need to make sure that these have weight so that these contribute once the MTF is outside of this range, like so. Okay, so if I evaluate the merit function, so that is 0. So this is because the specifications are met. So in order to kickstart the tolerancing so that it goes in the right direction, we can actually add some other operands which will guide the optimizer. So these are actually waveform calculation operands. So I'm just going to insert 2 more calculations. So this operand is RWCE, giving it rings of 3. So the idea of these, these will be in the documentation here, but we give them a low weight so that they contribute to the merit function early on. WCE, 33 rings for the chief rate, and low weight for this. So there's lots of flexibility to play around with weights to make sure your optimizations are going in the right direction. So I'm just going to refresh, and there's our merit function now. Okay, so then what I will do is open up the MTF analysis here. So we've already got one window open. So I'm going to move that here. I'm going to make sure that shows the on-axis field, like so. Then I'm going to clone, and I'm going to dock this next to the other MTF. And I'm going to make sure this looks at the off-axis field, like so. So this is to see the impact of tolerancing on the MTF when we evaluate the tolerances. So to do this, let's go on the tolerance tab. We'll go on to tolerancing. So in the first tab, zMAX provides several different tolerancing analysis tools. There's a sensitivity analysis, which is what we're going to run first, and this analyzes the performance of the system at the minimum maximum values, which parameter value. There's also inverse sensitivity, which is what we'll do afterwards, and this restricts the tolerances of each operand to not exceed the tolerance criterion. So if we select the criterion in the second tab, so here you have a large list of existing criterion, and you can define your own using tolerance scripts. You can see that there is a criterion for the MTF, but this is averaged over all the fields, and it does take longer to compute. So we'll select our merit function to just speed it up. Then on the third tab, we have settings for running Monte Carlo simulations. So what this does is it generates random lens files where each parameter is perturbed randomly within the allowable tolerance range. And you can also define the statistics with the presets here or use your own. So here you're accounting for all the errors simultaneously. So as a rule, you need to run at least the number of tolerances squared. So I would probably set this to a high number of 5,000 to really model the distribution accurately. But for now, I'm just going to run 20, and I'll also overlay the graphics so you can see with the MTF plots what is happening. So something just to point out, zMAX has a lot of features to increase the speed of tolerancing. For example, there is a polynomial setting where you can fit the performance curve to a polynomial so that when you next tighten the tolerances, the calculation is almost instantaneous because the criterion is now described by an equation. There's a tolerance cache, which saves time on recalculating tolerances for those that you haven't tightened. And in the computation, which is here, instead of using damped least squares, there is the paraxial focus. So this essentially does a quick focus and ignores other compensators. And there's also the quick sensitivity feature to check that you are getting your numbers in the right ballpark with your sensitivity. Okay, so let's run the sensitivity. So I'm going to use optimize all. I'm going to set for 3 cycles. Then that looks fine. So I'm going to hit OK. And you can see the MTF has degraded a lot. So we are below our specs. So what we can do is we can look at the tolerancing results here. Got the Monte Carlo raw results, the sensitivity, and then there's a nice summary here. So these are all the sensitivity analysis. So we can also look at the top 10 worst cases. So it looks like distances of the doublets around the stop and its tilt seems to be the biggest contribution to the degradation in the merit function. And here you can see that the merit function is degraded massively to 0.0 0.76. So we could tighten our tolerances by choosing precision or high precision in the tolerancing wizard here. But what I'm going to do is actually run inverse sensitivity. And to speed up the computation, I'm going to select the RMS wavefront. So first I am just going to, you can unlock refresh to reset the plots, unlock reset. So if we go on tolerancing, so we're now looking at inverse limit. Look at the criterion. I'm going to look at RMS wavefront this time because it's much faster. Look at 3 rings of 3 cycles, so I can click on check. And here we have 0.29 waves. So I'm going to set this to 0.3, which means no parameter will be adjusted beyond a value that will increase the nominal wavefront error by 0.3 of a wave. So I'm going to check that's what, yep. So I'm going to just run this. Here we can see that the MTF is much more bounded. And if we look at the tolerance data editor, the tolerances have been adjusted to new tightened ranges. So we can see that, for example, with the elements, the decentration has been restricted. So if we look at the report, we go back on summary at the bottom. So we can see that the wavefront error has increased from increased from 0.298 to 0.3. So that's quite a good result. So our system's behaving very nicely. So just to demonstrate with the Monte Carlo as well, with the results, usually you would run for far more files than this, but you can also look at yield. For example, with this number, 80% of designs would have a wavefront error of 0.47 waves or less. So if you were making mass production of designs, this is a good model for that. So what I'm trying to show here is that zMAX is extremely fast and flexible for tolerancing. Now, if you can't tolerance the design, zMAX provides many options. You can make any parameter a compensator using the CPAR operand. So compensators are great to relax the tolerances, but if you want to stay on good terms with mechanical engineers, do be aware that more compensators, sort of Teflon shoulders, the workload onto them. You can repeat the optimization. So one option, if I go on optimize, optimization wizard here. Optimization. So there is this very powerful feature called improved manufacturing yield, where the optimization goal specifically is to target less sensitive systems. In the merit function editor, you can also use the TOLR operand, where you can actually call the tolerancer from within the optimizer, and you can optimize the design for the best estimated performance. And then you can optimize across configurations to reduce sensitivity here. So what you can do, so for example, if the worst offender was a decentering and tilt of a lens, you can have 2 configurations going on the MC editor in setup. So you can add configurations where the other is your tilted lens, and you can optimize across these. And then there is the global search optimizer, which is great at finding variants of the basic design, and combining this with the improved manufacturing yield can give you a very insensitive system. With your final design, you can export this as an ISO element drawing or a general mechanical drawing. So if I go on tolerance, see here we can click on this, and let's just close these. Move that here. There we go. We can in fact import the tolerances from the tolerance data editor, and it will update the drawing. So if we go on reset from TDE, and there we have it. And then we can export the design to a CAD file. So in the File tab, here we have CAD files. And if zMAX can convert to a range of different CAD formats, like STEP, IGES, and STL. Okay, so next we look at another effect that can reduce the image quality, which is stray light caused by unwanted reflections, ghosting, scattering, and coupling. So the non-sequential mode in zMAX has many tools for stray light analysis and to reduce its impact. And what we'll do in this introduction is identify and quantify the stray light using the ray path analysis tool. So let's go onto our design. So we want to use a non-sequential tools. So we can convert this to non-sequential. And what we do first is if we go on tolerances and go on design lockdown, So I'm going to say what this does is turns any idealized settings in your design to realistic ones so that it better represents manufacturable design. So I'm going to create a new file. And this just means the glasses in the system will be replaced with the closest glass in the currently loaded catalog. So hit OK. And then what we're going to do is export the design rays so that we can examine these in non-sequential mode if we want to. So field wavelengths, we want those, and click OK. And then to convert to non-sequential, we simply go on File tab and convert to NSC group. Hit OK. Close that. And here we go. If we go on Setup, we can see that we're in non-sequential mode. And instead of surfaces, we now have sources, and we have 3D objects and detectors listed in the non-sequential component editor. So the fields are represented by elliptical sources, and detectors are placed at the focal point for each of the fields. We need an image plane detector, so I'm going to insert another line and detector color. So there's lots of documentation for all the different detectors. This would be for full field. And we're going to reference with respect to object 13, which is the position of our image plane. And for the size, I'm just going to set to 25 by 25 for now. So we can view the system by clicking on NSC 3D layout and also the shaded model. And with non-sequential, you can observe the rays splitting. So if we go on the settings of the layouts, if we hit split, NSC rays, and here you can see all the reflected, multiple reflections, transmission, reflection going on. And that's the core difference between sequential and non-sequential mode. Now, if we look at the sources producing the rays, there's a number of layout rays, which is what's shown on the layout, and then your analysis rays, so a number of analysis rays, and those are used for analysis at the detectors, and this is usually a large number in the millions or billions of rays. For now, I'm just going to set this to 10,000, just to save time, like so. And with ray splitting, you can get lots and lots of rays in the non-sequential design. In zMAX, in the non-sequential part of the System Explorer, there's limits on the maximum number of rays. I'm going to set these to maximum, so we get maximum rays reaching the detector. So I think the maximum of that was 4,000, and let's make that 2e to the 6. So this is to make sure that rays don't terminate before they reach the detector. And then in our image detector here, I'm going to set the number of pixels to 150 in X and Y. Okay, so, and to do the ray trace, we go on the ray trace button in Analyze, Ray Trace. We want to model the split rays, so we select that and clear and trace. Okay, that has finished. Hit Exit. So now we can view the results by using the detector viewer. So if we go here, detector viewer, and if we go on settings and select the image detector, detector 17, we'll take a log scale. Let's try log 10. I'm going to choose false color because it's pretty. Hit OK. Oh, that's quite saturated. So I'm just going to set that to be -3. There we go. And here we can see this low-level irradiance, which represents unwanted stray light. We're going to find out where it's coming from by identifying its ray paths, and we can use filter strings in the filter dialog box for the layout settings. So I'm going to include the split rays. So the filter strings, they have a simple syntax, and the full list of all strings can be found in the help system file. So for example, H17 tells us all the rays that hit object 17, which is our detector. You can combine the strings with logic operands. So I'm going to do andesand for logic and type G0 to look at ghost light from all objects. Hit OK. And so we've isolated those rays, and then we want to separate lights, the ghost light with more energy from that with lower energy. So we can do more filtering by actually increasing the minimum relative ray intensity. So I'm going to set that to a 5e to the -3. Okay, I'm also actually going to fletch the rays so we can look at their direction. You can also might need to refresh the plot a few times so it loops through those rays that fall within the filter. And so we can see that the strongest stray light is due to reflections from the front face, from the back face of this singlet, also the back face of this doublet. So one way to reduce reflection is to use anti-reflective coating on the lenses, and we can do this really easily. So if we go back on that, the lens on the left was object 6. Let's check. Yep. So I'm going to set 5 and 6 to have an AR coating on the back surface. So we just drop down, go on coat scatter, and I want the back face, and this is going to have an AR coating. And then similarly for object 5, back face, and we want AR coating for that. And also for the singlet, which is object 12. Let's just check. And that will be the front face and AR coating for that. Okay, so let's repeat the ray trace. First, I'm going to lock this. First I'm going to duplicate it and then lock this so that we can do comparison. So let's rerun the trace. And I'm going to save the rays this time. And let's hit clear and trace. And there we've reduced, so these are on the same scale, and there we can see that we've significantly decreased the stray light. So we can analyze the light in a specific area, and we're going to use these particular filter strings to do just that. So if we go back on the detector, we have this feature from -5 to 5 and from -1 to -4. And so I'm going to use these functions. So there's about 100 of them in the help system file to pick those rays within that area. So we saved the rays, and we can reload them. So if we go here, I'm going to set that back to e to -3. And yes, so we can reload our rays. Like so. And then I'm going to enter this filter string. And also I'm going to look at the first 50 rays, like so. And here we can see the where those rays are causing this feature on the detector. So we've found out what's causing this feature. So now that we know what's causing this, we can find out which have the most energy. So if we go on path analysis, and if we go on settings, we can actually just put in our our string, like so. And here we can see that 60% of the light in this filter is because of path 1. I'm going to leave it at that. Here's a summary. So just to point out that zMAX isn't scary. It's super fast. There's lots of documentation, technical support, and lots of presets. So it just makes design very seamless. And I hope you enjoyed this webinar. Thanks for your attention.